3 prisoners were sentenced to death. One of them French, one of them German, one of them British. What is your last wish? They asked the French guy. He says, a bottle of exquisite French wine. What is your last wish? They asked the German guy. He says, I want to give a speech. What is your last wish? They asked the British guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. Because I'm already in the middle of my little speech about the grand theme of our age, about the rise of artificial intelligence, which is going to transform every aspect of our civilization. There are other important issues, global warming, population explosion, and all of that is going to completely pale against this development. So this is my name. This is how to pronounce my name. And in the early 70s and 80s, I realized that the biggest thing that a man can do is really build something that's smarter than myself, such that I can retire. And this has been supported for a long time by a trend that has been active since at least 1941, when Zuse built the first working program-controlled computer. And since then, computing has become cheaper by a factor of 10 every 5 years. Back then, one could do about 1 floating operation per second. Now we can do 10 to the 15 times more for the same price. And this is a picture of my diploma thesis, where I, in 1987, for the first time, tried to build a general-purpose learning algorithm, which not only learned to improve in a certain domain, which was an old hat by then already, but also learned the way to learn, inspecting and improving the learning algorithm itself. I think that was the first work on something which is now called recursive self-improvement. We are most well known, however, for something which is called deep learning in artificial neural networks. Has anybody in this room heard about artificial neural networks? Hands up. Mm-hmm. Is there anybody in this room who has not heard about artificial neural networks? We have a third group. Who didn't understand the question. Here we have a recurrent artificial neural network, which is the most general, deepest type of neural network, which is modeled a little bit after the human brain. In the human brain, in your cortex, you've got about 10 billion neurons, and each of them is connected to about 10,000 other neurons. And some of these neurons are input neurons, and video is streaming into the neural network through your eyes, and auditory signals are coming in through the ears, and pain signals are coming in through your pain sensors and so on. And some of these neurons are output neurons, and they steer muscles. They steer motors in our artificial networks, which are similar in many ways. And now there are all these connections between these neurons, and each connection has a strength, which tells you how much does this neuron over here influence this neuron over there. And in the beginning, all these connections are random, and the network knows nothing. But then we have learning algorithms that over time make these networks improve and solve problems, such as translating the incoming video stream into sequences of motor actions that, for example, steer a car. And the cool thing is that we can learn these things from experience, either with teachers or without teachers. These are general-purpose computers, and we didn't invent deep learning because that was invented when I was a baby 50 years ago by a mathematician in the Ukraine. Ivagnenko was his name, and he had deep neural networks, feed-forward neural networks already in the 60s, half a century ago. But these were not recurrent networks, and the recurrent networks are more general than the feed-forward networks because they have these recurrent connections which allow the system to take the incoming video and store important things and through these recurrent connections such that previous inputs still circle around in memory, so to speak, and the network figures out over time which of these memories are important and which are unimportant. And so that's in the 1990s when we started this general purpose deep learning with deep recurrent networks. And maybe the most famous outcome of that is called long short-term memory, which is a particular network which doesn't have the problems of the old recurrent networks, and which back then nobody was really interested in that. But today, all the major companies are using it like crazy for all kinds of things, such as speech recognition, translation, all kinds of applications, because it's a really universal mechanism. Some people ask me, do you have a demo? And I just have to say, do you have a smartphone? Because each of you has a little piece of us in your pockets. Whenever you take out your smartphone and you don't type into it, but you use Google Voice or, on your Android phone, there's a little microphone icon there, and you speak into it instead of typing, what is happening? There is a long short-term memory network in there which has learned from nothing, from scratch, to recognize speech. And although the basic publications there date back to the previous millennium or the early 2000s, it took a while until computers were so fast that this method could unfold its potential. Until 2015, Google had a different thing for the speech recognition, but then they replaced that old thing by long short-term memory, the method that we have developed over the decades. And suddenly, they not only had a 5% better system, which would have been great, or a 10% better system, which would have been fantastic. No, it was really a dramatic breakthrough and was almost twice as good as before. And now it's pretty good. You can try it out. Don't do it now. What is happening there? Every 10 milliseconds, a new vector of numbers is coming from your microphone there and streaming into this LSTM, and then the network has figured out how to compute in a parallel sequential fashion what it should answer and how to translate that into a sequence of letters. First publication, 1997, first author, my very first student, Sepp Hochreiter, now professor, on my very first deep learning project ever. And Google is using that same LSTM not only for speech recognition, but also for the best translation from one language into another. How does that work? Well, you feed lots of sentences in English into that system, and you force it to output French sentences. In the beginning, the network doesn't know how to do that because all the connections are random. But then we have these training algorithms that make the network learn how to understand the syntax of English and the structure of French, and how to go from the meaning in English to the corresponding meaning in French. You train it on lots of examples. Before I came here, I thought this is going to be just a little tech talk and there won't be much of an audience, but you are actually a large audience by my standards. The other day I gave a talk at a conference and there was just one single person in the audience. A young lady. I said, young lady, it's very embarrassing, but apparently today I'm going to give this talk just to you. And she said, okay, but please hurry. I am the next speaker. The other thing that we did was take less general, non-recurrent, but feed-forward convolutional network and convolutional networks, which are a special type of neural networks, which goes back to Fukushima of the 70s and Weibel and LeCun in the 80s. And they used a method invented by a Finnish researcher, backpropagation, in 1970s. So all old stuff, basically, and combined that in a way that made it really fast on GPUs. GPUs are fast computers originally designed for the video game industry. And it turns out they are doing exactly the same massively parallel operations that we need to build fast neural networks on cheap supercomputers. And then for the first time, we were able to win competitions 5 years ago when computers were about 10 times lower than today for the same price. And we were able in 2011 to win this traffic sign recognition competition, 3 times better than the second best team, twice as good as humans. Humans were second best there. This is important for self-driving cars, of course, and here's the pioneer of self-driving cars, Dickmans. Some people think that Google invented this, but no. 20 years ago, in 1994, Dickmans already had fast cars, self-driving cars with cameras on the highway, often going for more than 100 kilometers without intervention of the safety driver who had to be on board for legal reasons. How many more minutes do I have? Where is my little sign? Do we have a little sign? Oh, there it is. Oh, I'm still green. Good. The same methods can be used to do medical diagnosis. Here we had a competition in 2012 where we were able to win brain scan segmentation tasks. And the same thing can be used, for example, to do cancer prevention. This is a slice through the female breast, and you see some cells there which are harmless and others which are not harmless, which are in pre-cancer stage, mitosis stage. And this means that you need a trained histologist, a human doctor, who looks at all these little things there and says, harmless, not harmless, 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 and so on. We train our stupid neural network to do the same based on lots of training examples from the human labeled from the doctor. And it becomes as good as or better than the best competitors and can rival human performance now. And this has led to lots of startups. When people realize that you can do medical imaging like this and you can take over certain aspects of being a doctor like this, lots of startups were created, and even the big companies, Google and IBM and so, went into that business. And why is that so? Well, why do they do that? Because the market for that is at least 800 billion per year. 800 billion per year just for medical diagnosis like that. Here's another thing that Google did when, with our CNN, GPU-based CNN, combined with the LSTM, the long short-term memory, which I told you about before. By the way, you know, the best thing about the LSTM is whenever you speak to your phone, we are getting a penny. Did you know that? No, I'm just kidding. Everything was freely published and everybody can use it, and Baidu is using it, and IBM and Microsoft, everybody. So down there you see an image which shows something, and down there is the caption which says, a herd of elephant is walking across dry grass. And you look at the image and you say, yeah, it's true. This was automatically generated. This was not seen by the system as it was trained. So it saw lots of images and captions downloaded from the internet, and then it learned over time to look at the image and then represent it internally in a way that was then fed into the LSTM, which rolled it out into a sentence, and it has learned to do image analysis and explanations in written form just from lots of training examples. It doesn't always work. Like up there you have 3 dogs playing in the grass, but the caption says 2 dogs playing in the grass. But you know, every 10 years we are getting a factor of 100. Every 30 years we are getting a factor of 1,000,000. And things are going to change dramatically in the near future. We had also very deep networks for the first time with more than 100 layers. We were training robots. We were, okay, so now, JC, please go 1 slide back, thank you. And maybe you have recently seen AlphaGo. AlphaGo is a system made by Google DeepMind, which is located in this city. And they outperformed the best human Go player using a neural network that learned by playing against itself, using a kind of traditional reinforcement learning method, which in similar form already was used in 1994 for backgammon. Backgammon was another game where a network learned to play better than the best human player, or as well as the best human player, through just experimentation and neural networks that figured out how can I beat my opponent, which in that case is myself. And Go, however, is clearly more complicated than backgammon, and several new tricks had to be invented for making that possible. Of course, I'm proud of that because DeepMind is a company which is heavily influenced by my former students. In fact, the first guys with PhDs in AI and machine learning at DeepMind, they came from my lab. One of them was a co-founder, got his PhD in Switzerland, for his work, and the other one, the first employee, Dan and Shane, and then later additional guys from my lab joined DeepMind. What you really want to do, however, is you want to go beyond traditional reinforcement learning, because with Go and board games, it's like that. You see the state of the world in a little thumbnail image, which has, in the case of Go, 19 by 19 black and white pixels, and that's what you know about the world, and all you need to know about the world is contained in there, because that information is enough to, in principle, to compute the optimal next move. In the real world, it's different. You get 100 million inputs through the pixels of your retina, and then you still don't know what's happening behind your back, because you have to memorize what you saw before behind your back to make sure that there's no line jumping at you right now. So you have to memorize previous things, and that's why we have worked a lot on recurrent neural networks that can then solve problems such as driving cars in video games. That's a picture from 2013, and my former RoboCup leader, he once was the world champion in the RoboCup, which is the most challenging robot competition. And there, each of these little robots actually has two systems on board. One is a model of the world that predicts what is going to happen if I do that, and it learns that from experience. And the other one is using the model to plan actions that improve the system. Now, what you want to build is a curious system, an artificially curious system that sets itself its own goals like a little baby, which is all the time inventing new experiments to better figure out how the world works by playing around. And that's what babies do, and our artificial systems are also doing that, because we figured out a way of making them curious and creative. There is no way of it's not true what you sometimes hear, that computers can do only what they are programmed to and they can't invent their own goals. No, that's exactly what our systems are doing. They are curiously and creatively coming up with new experiments where they actively learn to design experiments such that they learn more about how the world works, such that they can become better problem solvers. And all of intelligence is about problem solving. So we have little robots that learn like babies to play around and improve their skill set and increase their skill repertoire. And what is going to happen next? Well, I think in the not so distant future, for the first time in not so many years, we will have something like a little animal-like AI, which can do things that we see in crows and maybe little capuchin monkeys and whatever. Once we have something like that, the step towards human-level intelligence will be rather small, because it took billions of years to come up with a little monkey, but then just a few millions of years on top of that to add human-level intelligence. And technological evolution is much faster than biological evolution, so this is going to happen rather quickly. We have a company which is called Nascence, which is trying to make that a reality. It's pronounced like birth, like nascence in English, but spelled in a different way. Neural networks, NN, AI, artificial intelligence, because it's about the birth of a neural network-based AI. David, do I still have time for my exponential timeline, which shows how human history is about to converge, or do we have time for that? So. Some of you may have heard of the singularity, which is this idea of the technological singularity, which came up in 1950 or something, when Stanislav Ulam saw that the technological progress is happening faster and faster, and he said, if there's an exponential acceleration going on, then this must converge in finite time. And he said this endpoint is the technological singularity. And most of the proponents of this idea have focused on recent accelerations, such as Moore's law, or this thing which I mentioned at the beginning, every 5 years computers get 10 times faster. However, there is a beautiful pattern of acceleration which reaches all the way back to the Big Bang, which shows that the most important events from a human perspective, the most important events in the history of the universe are aligned on a timeline which corresponds to exponential acceleration, and I'm going to show that quickly to you. We start 13.8 billion years ago, and you will see that it's about to converge in the year 2050, which I call omega, the endpoint of human history as we know it. And I don't call it singularity. Instead, I call it omega, because Teilhard de Chardin 100 years ago called it omega. And And it goes like that. 13.8 billion years it starts. 13.8 billion years ago it starts, and then we take a quarter of the time, and from now on I'm always going to take exactly a quarter of the previous time interval. 3.5 billion years ago, that's exactly when life was invented on this planet, and we take a quarter of that time. Omega minus 900 million years, that's exactly when the first animal-like mobile life emerged. And we take a quarter of the time, and that's 220 million years ago when your ancestors were invented, the first mammals. And we take a quarter of that time, and that's 55 million years ago. That's exactly when your ancestors came into existence, the primates. And we take a quarter of that time, 13.5 million years ago. That's exactly your ancestors, the first hominids. And we take another quarter of that time, omega minus 3.5 million years ago. And that's exactly the dawn of technology, as nature called it 3.5 million years ago, the first stone tools. And we take a quarter of that time, and that's 800,000 years ago, the next great breakthrough in tech, controlled fire. And we take a quarter of that time, and it's 200,000 years ago, your ancestors, modern man, men like you and me. And we take a quarter of that time, and it's 50,000 years ago, the so-called behaviorally modern man coming out of Africa, colonizing the world. And we take a quarter of that time, it's 13,000 years ago, exactly the beginning of the Neolithic revolution, agriculture, animal domestication, and so on, colonization of the Americas. And we take a quarter of that time. That's the onset of the first population explosion in the Iron Age, about 3,300 years ago. And we take a quarter of that time, iron and fire come together in China to form guns and cannons and rockets and gunpowder and weapons and stuff like that. And we take a quarter of that time, omega minus 200 years. That's at the peak of the Industrial Revolution, the first Industrial Revolution in the 1800s, and at the same time, the onset of the second population explosion, which we are still living through. And we take a quarter of that time. That's omega minus 50 years. That's about the year 2000 with the information revolution, World Wide Web for everybody, cell phones for everybody, digital nervous systems spanning the planet. And we take a quarter of that time, and that's in the future. Omega minus 12 years or something. Maybe that's more or less when, for the first time, we will have human-level AI, and we take a quarter of that time, and you see, it's going to converge in 2050. What's going to happen afterwards? Of course, these guys are going to realize that most of the resources in the solar system are not in this thin film of biosphere around the third planet, but they are out there in space. Less than 1/1000th of the sunlight hits the Earth, and most of these resources will be accessible only if you go out there to exploit them. And there will be trillions of self-replicating robot factories in the asteroid belt. And of course, they will be scientists, and they will be curious, and they will set their own goals. And they will go out there and within a few million years colonize the galaxy, and is covered with senders and receivers such that AIs can travel the way they are supposed to travel, namely by radio from senders to receivers. And everything is going to change. Humans are not going to play a big role there, and they are not going to stay the crown of creation, but that's okay. We are be proud of being part of a grander process that transcends humankind. This is more than another industrial revolution. This is something that is comparable with the invention of life itself. And it's a privilege to live at this time and to witness the beginnings of that. Thank you for your attention.